My name is Jack Huerta, and I'm a candidate in the Scientific Computation PhD program at the University of Minnesota. Professor Lilja is my advisor. I'll be presenting the paper revisiting the effects of Spectre-Meltdown security patches. Operating systems are complex computer programs that are continuously evolving to accommodate changes and updates to the underlying hardware it runs on. Sometimes updates are released to address security issues. These fixes have the potential of affecting performance, and it is essential to gain an understanding on the effects that patches have on the system. Our work shows the relative effect the application of two of the Spectre-Meltdown fixes had on the system in terms of top-down bottleneck ratios. The exploits took advantage of CPU features that make it possible to use speculative execution to increase CPU performance. When the security patches were released, there were concerns that there would be a reduction in performance by possibly curtailing the speculation capabilities of CPUs. Previous works showed that there were small performance penalties when the patches were applied. We showed that while the overall performance was not affected for most benchmarks, the top-down bottleneck profiles were relatively affected. The Spectre and Meltdown attacks were discovered in early 2018, and they affected x86, IBM Power, and some ARM-based processors. The Meltdown vulnerabilities allowed an attacker to gain read access to all memory, even when lacking the appropriate privileges to do so. The Spectre vulnerability allowed attackers to gain access to private information through branch mispredictions. The Red Hat Linux vendor released its Spectre-Meltdown fixes, and included a feature to switch on or off two of the three patches. This feature made it possible to prevent a degradation of performance generated by the patches. The permanent patch addressed the Spectre Variant 1 vulnerability. It is a kernel patch that provides bounds checking during branching to prevent arbitrary bypassing. The other two fixes can be dynamically enabled or disabled. The Spectre Variant 2 patch includes a microcode and a kernel patch which prevent data leakage through indirect branch poisoning. The Meltdown Variant 3 is a kernel fix which prevents an attacker from reading memory through speculative cache loading. In this study, we use a top-down analysis method to identify dominant bottlenecks of a benchmark. This method tracks CPU slots, resources needed to process a micro-operation, and UOP. The top-down method classifies bottlenecks as non-stalls, retiring about speculation, and stalls, back-end bound and front-end bound. A simple classification is applied to pipeline slots to assign the bottleneck to its right category. If a slot was allocated, it will be classified as retiring. If the slot is eventually retired, it will be assigned to the bad speculation category if it is not retired. If the slot cannot be allocated, it will be assigned to the backend bound category if it is a backend stall. That is when there are not enough resources in the backend portion of the pipeline to handle new slots. Otherwise, it will be assigned to the front-end bound category. To better understand the effects of the security patches, we use a technique from the field of economics, purchasing power parity, PPP, to quantify the relative changes between performance metrics. The most well-known example of purchasing power parity is the Big Mac Index. The Big Mac Index is used to quantify the purchasing power of a currency in terms of Big Macs. Here's an example. We compare two Big Mac burgers, one priced in US dollars and another in Brazilian reales. The cost of the American burger is $3.57. Its Brazilian counterpart is 7.50 reales. The burger exchange rate is 210. We use this value to calculate the overall PPP rate by subtracting the actual currency exchange rate of 1.58 reales per dollar from the burger exchange rate. According to the Big Mac Index, the Brazilian real is overvalued by 33%. In this case, overvalue means its value in foreign exchange is more than it should be, based on economic conditions. There are two important concepts that need to be emphasized. Purchasing power parity allows for the comparison of the same good in different countries to see if a country's currency is overvalued when the good is more expensive, or undervalued when the good is cheaper relative to another currency. We adapted the PPP formulas to be used to compare top-down metrics. Instead of burgers, we're comparing programs whose cost is reflected in performance metrics. The currency used for comparison is the CPU cycles it took to run the program to completion. CPU cycles are the denominator of the top-down metric ratios. We compare the cost of the program when patches are enabled to the results of the same programs when patches were disabled. CPU cycle values when patches were disabled were used as the baseline for comparison. Equation 3 shows the computation of the PPP exchange rate in terms of CPU cycles. Equation 4 computes the actual normalized PPP rate. The baseline represented by the variable metric baseline was the resulting top-down metric value with the security patches disabled. The equations for the top-down metrics were included on the paper. PPP rates can fall in three different categories. PPP normalized rates close to 0% imply parity in the performance metrics between the baseline run and the run with the security patches enabled. There's relative little difference between the two patch settings. Negative PPP rates imply that the CPU cycles for the run are undervalued. It requires more CPU cycles to complete the same performance rate when compared to its baseline run. For positive PPP rates, it implies that the CPU cycles are overvalued. The new run requires CPU cycles to achieve fewer CPU cycles to achieve the same performance rate when compared to its baseline run. For our experimental setup, we use the Spec OpenMP 2012 benchmark suite. This is a highly scalable set of benchmarks made available by the Spec Consortium. OpenMP 2012 results that follow the Spec reporting guidelines can be submitted for publication in a public repository. We use a dual-socket Xeon 4110 CPU with 32 threads with hyper-threading enabled. We compare the Intel 2021.1 compiler suite with patches enabled or disabled. To disable or enable the patches, we added a 0 or 1 to 3 files: IVRS enabled, RATP enabled, and PTI enabled. Here are the runtime results for the OpenMP 2012 benchmarks. There were at least 55 runs for each benchmark for each patch setting. When the patches were enabled, most benchmarks experienced an average of 0.01x speedup loss. Only 370.mgrid331 had a larger negative effect, which was closer to a 0.04x speedup loss. We next show the effects of patches had on the 350.md benchmark. We reviewed 2 of the 4 top-down categories. These metrics were computed using the average of the different performance counter values that are used in the top-down formulas described in the paper. Here we have the results of the value speculation top-down category for the 350.md benchmark. This is a molecular dynamics simulation program. Bad speculation accounts for the slots that were wasted due to incorrect speculation. This category will be affected by the Spectre-Meltdown patches. Here we see that there was an increase of 101% when patches were enabled, while its PPP normalized rate was closer to 60%. This is due to an increase in the number issued UOPs and the number of stalls due to recovery from an earlier branch misprediction or machine clear event. In this case, the CPU cycles were overvalued. The retiring category represents the fraction of pipeline slots of useful work, the UOPs that were eventually retired. The retiring metric value decreased for the 350.md benchmark by about -20% when patches were enabled. This is attributed to an increase in core cycles while the number of retired slots remained relatively constant when patches were enabled. The corresponding PPP normalized rate decreased by about -40%. The CPU cycles are undervalued. More cycles are required to do an equivalent amount of work when compared to its baseline. Here are a few takeaways. PPP normalized metrics make it possible to identify relative differences between rates. It makes it possible to distinguish between similar rates, and rates that are different can be amplified or reduced. In this study, we analyzed the effects that the Spectre-Meltdown security patches had on CPU pipeline bottlenecks. We showed that bottleneck profiles can differ even when security patches had little effect on performance. We showed that relative rates can vary significantly, while absolute bottlenecks rates can remain relatively similar. We highlighted trends and differences in metrics that might have otherwise gone unnoticed by standard evaluation practices. We were able to quantify the relative changes when compared to a baseline run. Additionally, the use of PPP normalized rates made it possible to put into context the large percentage changes reported by the relative difference between metrics. Performance optimization and characterization can be a complex task. Having access to precise information on the effects changes had on the system will make it easier to ascertain how the different subsystem components are being utilized. The use of techniques such as purchasing power parity can make it possible to obtain a more complete and accurate picture of the effects security patches had on systems. Thank you.